Hi guys, and welcome to this lesson on maths where we are going to be looking at calculus. We're going to be looking at some of the big concepts that you learned in grade 12 and those concepts that are super important for your final exam. Let's get started. Okay, so one of the big things that you learn first is deriving by first principles. Of course, this involves the concept of a limit, and there is a special formula that you use. So the formula we use to find the derivative by first principles is f prime x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that formula is what we call the derivative by first principles. And when we use this formula, we have to be very careful that we keep the limit as h approaches 0 in every line of the derivative by first principles. Do not lose the limit as h approaches 0. There are also different ways that we can represent that we are finding the derivative. If we use the functional notation y is equal to f of x, then we can say that f prime x tells me that I'm finding the derivative. Y prime also tells me I'm finding the derivative. D of x or differential of x or dy dx all tells me that I'm looking for the derivative. Now those symbols d and d dx are called differential operators. And the reason we call them differential operators is they tell us that we are differentiating whenever we see them. Remember that dy over dx is not a fraction, so this is not a dividing line. All it tells us is that y is being differentiated with respect to x. So similarly, if you saw dt over dx, that will tell you that you're differentiating t with respect to x. Now you guys need to know all the different ways and the different notations that you can represent that you are finding the derivative. We know that using first principles is a very long method, and while if the question asks you to derive by first principles, yes, you'll have to use first principles, but if the question does not state that you need to be using first principles to derive, then you can use the rules of differentiation. Okay, so that first principles formula is quite a long one. You do need to know it, and you need to be able to apply it if the question asks for it. Otherwise, we can use the rules. So what are the rules? You guys would have learned about the constant rule. And remember, all these rules make it simpler to find the derivative of a function, but it gives you the same answer. If you've got f of x is equal to some constant c, where c is a number, then f prime x, the derivative of f of x, is equal to 0. So for example, if f of x was equal to 2, the derivative would be 0. The power rule is one that we use quite often. If f of x is equal to x to the power of n, then the derivative is equal to n times x to the power of n minus 1. That n there is any real number, but it's never equal to 0. The sum and difference rule, so it's just as when you're working with functions, it's easier to find the sum and difference of functions using those rules. Similarly, in derivatives, we look at the sum of a derivative is equal to, so the derivative of a sum, is equal to the sum of the derivative. So if you have the derivative of f of x plus g of x, that basically means you're going to find the derivative of f of x, and then you're going to add that to the derivative of g of x. Similarly, the derivative of a difference, so that's where you see a subtraction sign, that is then equal to the difference of the derivative. So if you have the derivative of f of x minus g of x, then that is equal to the derivative of f of x minus the derivative of g of x. And we know, and we've also been applying this, the last rule, which is that the derivative of a constant k multiplied by a function f of x is equal to the constant multiplied by the derivative. So what that basically means is, say we have f of x is equal to 2x cubed, then we can say that the derivative f prime x, or the derivative of f at x, is equal to 2, so it's your constant, times the derivative of f of x. All right. Now, when do we differentiate using first principles? As I said before, if the question says use first principles, you have to use first principles to get full marks. Also, they could say use the definition of derivative. That also means use first principles. If the question says nothing at all, then you use the rules for differentiation. All right? What is so essential, guys, and I cannot stress this enough, is that you have to understand exponents to be, I would say, more skilled, or to have a better understanding of the rules of differentiation. You have to have a good knowledge of exponents. So before deriving, we also need to remember our exponent rules. And when we start deriving, there are certain things that we need to make sure happens in the function that they've given us to derive. So what are those things? Well, before you derive, you need to make sure there are no variables in the denominator. So say you have a function f of x is equal to 2 plus 1 over x. The first thing you need to do is you need to get rid of that variable x in the denominator. How do you get rid of it? That's where your exponent rules come in. So you need to change 1 over x to x to the minus 1. So we would rewrite this as 2 plus x to the power of minus 1. So there's no variable in the denominator. You also need to make sure that there are no surds in your expression before you derive. So if I have, for example, f of x is equal to x squared plus the cube root of x to the power of 4, I need to get rid of this surd. Okay, how do I get rid of it? Again, we have to use exponents. So what does my exponent rule tell me here? Well, to change the cube root of x to the 4 to exponential form, you rewrite this as x to the power 4 over 3. And what you'll see happening there is the number inside the surd becomes the numerator, and the number outside in the tail of the surd, the 3, that becomes your denominator. Once we have our function in that form with no surd, then we can derive. You've also got to remember that if there are any brackets, you need to remove them by expanding or simplifying. So say I had g of x, and I'm being asked to derive. Obviously, in all of these cases, you've been asked to derive. So if I have g of x is equal to x plus 2 squared, and the question says find the derivative of g of x, you have to expand that x plus 2 squared first. So you'd use what you know about squaring a binomial. So you'll first simplify this to x squared plus 4x plus 4, and then you will derive. And then you'll see I left out the other point there. There are only separate terms before you derive. This is where this comes in here. We can see that we have separate terms. Remember, terms are separated by pluses and minuses, and here I've got separate terms, and then only can I derive. Okay, so those are some important things you need to remember of how you should simplify before you take the derivative. Also, I just want to touch on this. If you have a fraction, like we said, no variable in the denominator, if there is a question where you need to simplify, let's just do that quickly. So say I have f of x is equal to 4x squared minus 9 all over 2x minus 3. To simplify this before getting it into the point where you're ready to derive it, you first need to factorize the numerator. So you need to remember all your rules for factorizing. This is where your algebra from grade 9 becomes so important. You have to first factorize the numerator, see that that's a difference of squares, cancel out your like terms, and then only can you derive. So like I said before, there has to be separate terms, only pluses and minuses, no division lines, no surds, and no variable in the denominator. All right, let's talk about tangents. We know that a tangent is a straight line that touches a curve at just one point. So if I have a curve, a tangent will touch that curve at just one point. The gradient, what we've also seen is that the gradient at a point on a curve is the same as the gradient of the tangent to the curve at the given point. In other words, the gradient of my cubic function here would be the same as the gradient of the straight line. So if we have a tangent to curve f of x at a point, so say this is the point A with coordinates x1, y1, then the straight line that's going through that point A will have the gradient given by the derivative of f at that point x1. So basically what that means is if I know what the x coordinate is at that point A, all I need to do to find the gradient of the tangent at that point is take the derivative and then substitute the x value into that gradient formula. All right. So how do we find the equation of a tangent then? Well, we said it's a straight line, so therefore the equation is going to be given by the function y is equal to mx plus c. So we said we know how to find the gradient, we find the derivative at the point, and then what we need is to find the y-intercept to give us the equation of the tangent. How do we find the y-intercept? They will give you another point, or they will give you that point A, where the graph, the straight line, makes contact with the function, and you can use that point to find the y-intercept c. All right. So let's quickly go over equation of a tangent. To find the equation, we find the derivative using the rules for differentiation. Then we substitute the x coordinate of the given point into the derivative to calculate the gradient of the function. So that was f prime at x1. We're substituting the x value there into the derivative equation. We then substitute the gradient of the tangent and the coordinates of the given point into the y equals mx plus c formula, and then make y the subject of the formula and write the equation in standard form. All right, so that's one of the key concepts you learn, finding the equations of tangents to cubic functions. That's one of the key things you learn in grade 12. Some of the other things that we learn about are maxima and minima and optimization. We also learn about finding rates of change, and the most important section in calculus is obviously cubic functions. We're going to talk about all of those when we come back after this quick break. Welcome back, everyone. So glad that you've come back to join us with our calculus revision of the big concepts, the big ideas that we need to know before we write the final exams. So I was saying to you that one of the big concepts that we learn in grade 12 is all about maxima and minima. So it is one of the most important applications of calculus because we use it to do things like maximize profit, minimize costs. Okay, so you will see this across all sorts of different fields, especially in manufacturing, where we want to minimize the amount of material used to manufacture, for example, an aluminium can. If we reduce the amount of material used, we can reduce the cost of production. All right, so problems that require some variable to be maximized or minimized is what we call optimization problems. So to find this optimum point using calculus, there are certain steps that we use. The first thing we do is we let the derivative equal 0 and we solve for x. So say, for example, the question said, what is the dimensions that will minimize the area to be fenced in if we're talking about a garden that we want to fence in? Well, the first thing we'll do is we'll find the derivative of the function we are given, set it equal to 0, and then solve for x. Then we need to check whether that point we found is a local minimum or a local maximum, but without drawing the graph. So how do we do that? We find the second derivative. Okay, second derivative basically means you take the derivative of the derivative. So f double prime x, if it is less than 0, in other words negative, then that point is a local maximum. If it is greater than 0, then the point that you found is a local minimum. All right, so the problem-solving strategy, you really cannot learn this off by heart. You can do lots and lots of practice questions, and it will help you to get better at problem-solving strategies, but this is not something that you can learn off by heart. The only thing you can do here is to have some sort of general guide, which is what I'm giving you now. Okay, so the first thing we make sure we do is we read the question carefully, we draw a diagram if we need to, and we decide on the variables that we need to use. Once we've done that, we determine what quantity it is that they need us to maximize or minimize. If necessary, then we write a formula for that quantity to be maximized or minimized in terms of the variables that we've already decided on. The quantity that needs to be minimized or maximized, when we get to this point, once we need to derive, you need to be very, very careful with this. Once you're needing to derive, you need to make sure that that quantity that you are maximizing or minimized is expressed in terms of only one variable. So your whole equation needs to be in terms of x or y or whatever the case is, whatever variable you are using. You write any other information that relates the variables in another equation. Okay? We then find the derivative, set it equal to 0, and solve for the value that will minimize or maximize the problem. You then find the second derivative to see whether the value is a minimum or a maximum value. Okay, and then another very important application of calculus is rates of change. This is what makes calculus ever so useful. How fast are things changing? One of the most important applications that you do in grade 12 is velocity. Velocity is, of course, the rate of change of distance over the corresponding change in time. So if we take the derivative of velocity, we find acceleration, or the rate of change of velocity. So this is what we generally do if we've got a function s of t, which gives the position of an object at time t, then the velocity of that object will be vt is equal to s prime t, depending on what variables you've been given, s prime t or ds over dt. The acceleration of the object is given by the second derivative, so it's s double prime t. Okay guys, so we want to talk about, and this is where we're going to spend quite a bit of time, cubic functions. It is the most important aspect of calculus in grade 12. Okay, so we know that cubic functions are of the form f of x is equal to ax cubed plus bx squared plus cx plus d. That power there, the power of 3, tells me that this is a cubic function. It also tells me at most, when I'm finding my x-intercepts, there will be at most 3 x-intercepts. The shape of a cubic function is what you need to be able to sketch the cubic function. There are basically 2 shapes of cubic functions depending on what the coefficient of x cubed is. So if a is positive, then the graph starts out concave down, as you can see what I've drawn here, concave down, and then it ends up concave up. So you can think of it as the graph starts off sad with maximum problems and then ends up happy with minimum problems. Okay, so that's if a is greater than 0, so in other words, positive. If a is less than 0, then you have a graph that starts out concave up and then it ends up concave down. So you can see we start with a minimum, local minimum point, and then we end on a local maximum if we're thinking about the turning points and the shape that we are looking for with this graph. Okay, so when a is less than 0, we get a graph as I've shown you. First we have a local minimum followed by a local maximum. We also, instead of using the word local, we use the word relative because those are relatively maximum or minimum values. In other words, what we're saying is there are values that are higher or lower than those stationary points that we found. So that's what we call a relative. It's relatively maximum or relatively minimum, those x and y values, depending on what you have found. But it is not an extreme point. An extreme point being a point that will have a high value or a low value, and those values can be lower or higher than whatever you found for your turning points. Okay, so these points are called relative minimums and maximums. Okay, so for example, if we think about it, if this is our maximum turning point there, you can see that there's a value on your graph up here that would have a higher y value than whatever the y value is there. Similarly, this is your relative or your local minimum, but there will be other y values that come below the graph. Obviously, this continues forever. Okay, so that's just a good thing to know. So how do we sketch a cubic function? Well, firstly, we look at the shape. If A is positive, we know what the graph's going to do. If A is negative, I've shown you just now what the graph's going to do. You then need to find the x-intercepts. Remember to find the x-intercepts because we're dealing with a cubic function. We let y equal 0 and we factorize using the factor theorem. We then find the y-intercept by letting x equal 0 and solving for y. And then importantly, we need to find the turning points, or what we call the stationary points. So the turning points, remember, we call them the stationary points. At most, in a cubic function, there will be 2 turning points, depending on whether your shape is such that a is less than 0 or a is greater than 0. You'll know whether you're having a minimum followed by a maximum or a maximum then followed by a minimum turning point. But there'll only be 2 of those at most. Remember that the gradient at those stationary points is 0, so you can think of a stationary point as a point where the function stops increasing or decreasing. There are 3 types of stationary points: the local maximum or local minimum, and I've explained to you why they're called local, and horizontal points of inflection. So what we need to remember is that the gradient of a function changes on either side of a local maximum or minimum value. So as you can see here, my gradient, if we follow the graph up until the point where we get to the local minimum, there, if I had to draw a tangent to this graph, the gradient anywhere off that tangent up until we get to the local minimum value, the gradient will be negative. And then if we go up to the point where we're going to the local maximum and we draw a tangent line to that graph, the gradient will be positive. So what we can see is that the function changes from decreasing to increasing at a local minimum. So there we go. You can see the function was decreasing there, and then it starts increasing, and that's at a local minimum. And then when we're looking at a local maximum, we go from an increasing function to a decreasing function. To determine the coordinates of stationary points, we find the derivative, let it equal to 0, solve for x, substitute those values back into the original equation, and find the y values. All right, points of inflections are extremely important. We know that the gradient on either side of a horizontal point of inflection stays constant, so that's as shown. There's positive gradient, so the gradient is continually positive. The graph, therefore, is increasing, as you can see, on both sides. So as x increases, y increases. So this is an increasing function. Guys, while we're talking about points of inflection, remember to find your point of inflection on a cubic function. That's when you let the second derivative equal to 0. So you'll say f double prime x is equal to 0. So you find the derivative of the derivative. Another way that you can find the point of inflection, so say I have this graph. So I've got a graph like that, and we know the turning point there is 0, 5. And we know the turning point here is 1 and 4. And say this is the function y is equal to, so you can check this for yourself, 2x cubed minus 3x squared plus 5. So I can certainly find the point of inflection by letting the second derivative equal to 0, or I can find what value lies midway between the x values of the turning points, and that will give me my point of inflection. So for example here, I see that my x-coordinate of the local minimum is 1, and the x-coordinate of the local maximum is 0. So to find my point of inflection, all I would do is I would add the x values together and divide by 2, because the point of inflection lies midway between your maximum and minimum values. All right, so 1 plus 0 divided by 2 gives me a half. So my point of inflection would be x is equal to a half, and you can actually check that with this function I've given you by finding the second derivative, and you will see that you will get this point of inflection being a half. All right, so I quickly want to touch on concavity. We know that the sign of the second derivative shows where there's a change in gradient of a function, and very importantly, if the second derivative is negative, the graph is concave down, so you can think of it almost as your cup being turned over. If you draw tangent lines to this graph, it will lie above the graph. If the second derivative is positive, the graph is concave up, so your cup is now full with liquid, it's not going to pour out. if you draw tangent lines to the graph, they will lie below the graph. And of course, if the second derivative is equal to 0, then we are looking at a point of inflection. Okay, importantly, at a point of inflection, the gradient of the curve is constant on either side. All right, thank you so much for joining me today. I hope that you've learned a lot about what ideas you need to keep in mind to write your final exam, and good luck.